Hey, my name is Shannon. This is my genius son, Isaac. Uh, our YouTube channel is
Train of thought.
Science. Tonight we're going to be talking about Heisenberg uncertainty principle and uh, in related subject matter. Okay, Isaac. Okay. Heisenberg.
Okay. You want to read that while I get over this?
Okay, Werner Heisenberg developed these principles in 1927. The most well-known variation was developed by Erwin Schrödinger in 1935. In modern society, this concept was made famous mainly by the Big Bang Theory TV comedy and the episode The Tangerine Factor. The idea was you had a cat in the box and you didn't know whether it was alive or dead. And until you open the box, it is in a position of both states.
So we've got this OneNote account. That's where I'm keeping all this. But hang on. First, which one should we do?
Okay, we're back.
So, this uncertainty principle is main in the quantum world. Quantum means smaller than atomic. No, not atomic. Quantum is smaller than microscopic. So molecules and stuff, it's smaller than that. Quantum would be atoms, electrons, neutrons. And one of my favorite effects is quantum tunneling, and that's when a quantum particle actually borrows energy from a structure like a table to pass straight through it. It borrows energy, and right before it leaves, it'll give the energy back, so it can pass through solid objects. So what's the next effect?
The next effect? I don't know. You're the one who did the homework on this. This is unfamiliar territory for me.
Okay, so there are two theories as to the makeup of quantum mechanics. So you have atoms, and then you have electrons and muons and all that. But the smallest thing is still unknown. There are a couple of theories. There's Calabi-Yau manifold, and then quantum foam and strings. Wait, that's how you spell Calabi-Yau. I think it's pretty good already.
Okay.
But there are actually 11 known dimensions. 6 are hidden, and the 5 base dimensions are length, width, height, time, and then the 5th dimension is actually a theoretical dimension that unifies the 4 forces of the universe. That would be weak nuclear forces, strong nuclear forces, gravity, and electromagnetism.
That's the fifth dimension? Okay.
And gravity is actually a pretty weak force. One theory, actually, before we get to that, I'll have to describe Calabi-Yau manifold. The Calabi-Yau manifold is the 6 hidden dimensions folded onto each other into an infinitesimally small particle. So that's 10 to the negative 33 centimeters in length, or in diameter. So a centimeter is 100th, and 10 to the negative 33 is 32 zeros. So you get 1/10 of a meter.
But you said infinitesimally small.
Yeah.
That would mean that you couldn't put a measurement on it because
Not
once
literally
you put
infinitely small.
Okay.
Perceptibly.
Yeah, I'd
But
say
it's
so.
1/10 of a meter in diameter. And it's just basically the 6 hidden dimensions are rolled up. I'm going to go ahead and blow up this picture. That's a demonstration of the Calabi-Yau manifold. So there are actually tens of thousands of varieties of this, and string theory, which I'll explain in a minute, does not string theory does not show which one is correct, so there's absolutely no way of knowing which way of folding the 6 dimensions is the actual way that the manifold is. But it's the only way to preserve the supersymmetry at the same time properly demonstrating all 6 dimensions. Supersymmetry is a state in which the equation of the forces and the equation of the energy are the same. Forces and energy. Forces and matter are identical. So that's supersymmetry. So now that I've explained that, gravity can be really weak because the gravitons are actually a theoretical particle, the particles that carry gravity. They pass through the Calabi-Yau manifold into the 5th or higher dimension. So, like he was...
You're saying the Calabi-Yau manifold makes up the quantum foam?
No, we'll explain quantum foam in a minute. But
Okay,
I'm saying...
But they're not, these are two different theories, they're not really related.
Yeah, but I don't think Calabi-Yau manifold is a theory, I'm not sure, because it's the only way to fit
Mathematically...
the extra 6 dimensions.
Okay. And then there's quantum foam, right?
Yeah. But the graviton leaks into the 5th or higher dimensions, and as we were talking about earlier, that's a shadow of gravity onto our dimension. That's one theory as to why gravity is very weak. It's much weaker than any other of the forces, because if you take a magnet to a paperclip, it lifts so easily. And considering the size of the Earth, the magnet should not be able to overpower the gravity of the Earth. But considering gravity is weak, it picks it right up.
If it were equal, we'd be in trouble. If gravity were equal to the magnetic force.
I don't think we'd be in trouble if it were, then we would have evolved much differently.
Well, if we did evolve differently, we'd be like this tall and spread out. You understand?
Yeah.
If you have a magnet the size of a planet, it's a lot of magnets.
Like we said, neutron stars in our first video. Quantum foam is a theory of elementary particles that are going in and out of existence. You hear about outside of the universe, there are particles blinking in and out of existence. That's called virtual particles. But the, quantum field theory doesn't deal with particles with enough energy to actually go out of existence, because that requires a lot of energy. So it's an extension of the quantum field theory. And that's quantum foam. And then string theory, it states that everything is made up of vibrating strands of energy. But since they're so small, like I said, 1/10 decillionth of a meter, it requires a whole bunch of energy. And I read that it requires as much energy as a train, but that doesn't sound right.
For a single string?
Yeah, as much energy as a train. That doesn't sound right, but the point still remains that it requires a huge amount of energy.
It sounds feasible. I mean, you think about how much energy is actually contained in, let's say, an atom. I mean, you split an atom, you have an atomic explosion.
Yeah. Split just a few atoms and you have one of those huge explosions because there's so much contained energy.
Mm-hmm.
Same with the contained energy in that one chemical compound is azide.
Mm-hmm.
You want to go into that or just move on?
Yeah.
The energy of the vibration actually determines a lot. If they're vibrating really fast, then that determines the weight of the particle. So copper is heavy, and other materials like iron can be heavier materials. That's because the strings have a higher vibration. Assuming string theory
Copper's
is
playing
true.
heavy metal. The strings. The vibration of strings.
Not to consider it's heavy. But it actually naturally explains gravity because the vibrations the vibrations of the strings create the exact same characteristics of a graviton, which are theoretical particles that create gravity. And more on the uncertainty principle is actually developed. Good catch.